Good afternoon, everyone. So welcome to the seminar. Today it's my pleasure to introduce our speaker, Dr. Tanja Rauch-Williams.
Good enough.
Yeah. Dr. Rauch-Williams is the Chief Innovator Officer at the Metro Water Recovery. That's the largest water and resource recovery agency in the Rocky Mountain West area that serves more than 2.2 million people. And she has more than 25 years experience in wastewater treatment, water reuse, and applied research, with strong expertise in nutrient removal, resource recovery, energy optimization, and trace organics. So today, she will share perspectives on upcoming nutrient removal challenges, future regulations, and how utilities are using innovations in treatment process and operations. So please join me a warm welcome, Dr. Rauch-Williams.
Thank you. And everybody can hear me okay? Good. And online as well? I heard at least one cling that somebody is online. I'm not sure I should take that as a yes.
Yes.
We're good?
Yeah, I think so.
All right.
You tested the voice.
You tested it. Very good. Thank you. All right. So I'm Tanja Rauch-Williams. Thank you for the introduction. I'm glad to be here. I think maybe one or two were in a seminar I gave for in Ashwin's class. Let me just get an overview. Before I start diving in, it's always helpful for me what actually interests you. How many of you are environmental engineers and are interested in wastewater? All right, at least half of you. My challenge will be to not make the rest of you fall asleep. So tell me, maybe a couple of you who didn't raise their hands, what are you working on? Is it more hydrology? Because I know there's hydrology and water resources. How many are doing water resources? Fair amount of other. Okay, good. That's actually then maybe. And who does neither one of the two? All right. What are you interested in? Civil, I have civil stuff in here. We do civil in the wastewater treatment plan. That's good. All right, let me start with that. A few of you know me well, and you know that you can ask me any questions at any point in time, whether they are left field, whether you think, I'm not sure this is an intelligent question, ask it anyway. That's why we're here. So at least it helps me connect to where you are and what I'm talking about and keep you engaged. If you start to fall asleep, think of a question and bring me back to something you like, okay? So I work in with Metro Water Recovery. Who has never heard of Metro Water Recovery? That's fair enough, because you're up in Fort Collins, you have your own wastewater treatment provider here. Hopefully you have of you who have done wastewater treatment have had a chance to visit Mulberry and saw that facility. We're essentially the Mulberry of the Denver metro area. And so we are serving, let me just get to the first slide here. We are serving the larger metro area. There's a few islands in metro and the Denver metro area who are not serving, and we get every year requests, can we join your district? From those who are not yet in our system. The reason being that wastewater treatment and the costs is becoming quite expensive. We have a number of utilities that are older that would need to make major investments to comply with future regulations. And at times it is easier to buy into our system, even though the cost is also significant, but to give, up the regional plans, which from a water resource planning is actually quite interesting, I find, because we're really centralizing. We pull all this water together, put it into our outfall. It's now in the South Platte. We essentially, for large parts of the year, are the South Platte River. And a lot of the other areas get a little drained with water because we're not having these other discharge locations any longer. We're treating currently 140 million gallons per day. We're designed for 220, so there's still quite a capacity. We have two major treatment facilities, the Robert W. Hyde treatment facility, somewhere quite next to 270, if you ever drive that insanely stuck up road highway. Excel is there with a chimney, and Suncor. So we're right in that industrial area in the middle on an island so to speak. I'll show you this in a second. And then we have a smaller facility that's closer to Fort Collins. It's in Brighton, the Northern Treatment Plant, which is a smaller regional facility that was designed about 15 years ago to capture a number of the flows from that northern part of the metro area to bring it there. That facility is also very quickly picking up flows. And already we're talking now about expansion of this facility and when that is required. So in this presentation, I thought, because nutrients seem to be interesting, I didn't put a lot of words on regulation on here. I know there's an interest in regulation, so I'll bring this in, or please ask me a question if I don't do it enough. Regulations in Colorado are really interesting and very unique in the US context. And there is right now a lot of development related to nutrient regulations, which make a very big impact on utilities, on communities. To just give you an order of magnitude, Micah is right now doing a PhD with us, focusing on treatment challenges related to nutrient that cost Metro, if we did what the regulators wanted us to do, over $1 billion in infrastructure improvements. Difficult from a financial side, very difficult from an infrastructure sequencing side. And needless to say, there's a lot of job opportunities in the future for you to help figure out how to go sustainably and financially sustainably about those challenges. So in this presentation for about the next half an hour, I want to give you somewhat of a synopsis of nutrient removal at Metro. First, I want to talk about what the conventional way is that most utilities treat nutrients. Hopefully some of you have seen that in your classes. I want to show you what Metro did in the last 10, 15 years, because they put in a number of very unique technologies to save costs, save footprint, and intensify the treatment. And then I want to talk about what the next generation of technologies are that we need to look at now and that we're researching specifically in my department, which is the Technology and Innovation Department at the utility. And our job is to look at what is the next frontier, how do we do it intelligently so that we give recommendations to the engineers and the operators in our facility to put the right projects on our capital improvement plan. In terms of regulations, we started out about 15 years in the state. You may have heard of what we call Regulation 85. It was a very broad technology-based regulation that essentially required utilities, anybody larger than 2 MGD, to implement nitrogen removal and phosphorus removal. And so over the last 15 years, we as utilities and consultants have really worked on a lot of the facilities, including yours here in Fort Collins, on implementing denitrification and phosphorus removal to get just a general broad reduction of nutrients below 50 milligrams per liter for total inorganic nitrogen and less than 1 for phosphorus. So that is now in our state, the state of technology. We are looking in the future to in 2030, I put in post because a lot of this is right now in negotiation with the state, how we actually go about it, but going to tighter ammonia-based limits based on aquatic toxicity of ammonia. We updated the toxicity model in past years, and so have tighter limits, acute and chronic limits for ammonia that we need to comply with. And then ultimately, we are right now in our state debating heavily, how do we meet the in-stream standards for nutrients? We have standards that EPA is setting and that CDPHE enforces in the permits to meet essentially water quality requirements for chlorophyll A and for eutrophication in lakes and streams, rivers, etc. And those are very tight: total nitrogen less than 2 milligrams per liter and total phosphorus less than 0.17. So we'll talk about that in the very end of my presentation, what we're doing to get there. All right, so in terms of an overview of our facility, I mentioned we're somewhat in an island because we are bracketed by the South Platte, this channel down here, Sand Creek coming in, And so our treatment facility is somewhat landlocked. We still have space for expansion there, but not a lot. We're already starting to prepare moving a number of these buildings out for expansion in the future for additional treatment requirements. Very large scale. The geography of our site is that we have 2 liquid stream facilities. So we have what we call the northern treatment plant, the north secondary treatment complex. North is here, going this way, and then the south treatment plant. And then in the middle, we have the solids treatment. So primary sludge, secondary sludge is brought into the digester complex here for stabilization. The solids of which, when they are stabilized, are being trucked out to a farm. We have 50,000 acres of farm where we grow grain for food production with those biosolids. We talk a lot about the secondary process here because this is really where nutrient removal begins. To give you a little overview and orientation, these are the aeration basins in which we're doing nitrification, denitrification, and phosphorus removal. And then here, likewise, it's a different layout, but here are 6 aeration basins. And we'll talk a lot about these little tanks. Here, there are 4 tanks up there because they are really a powerhouse for us for nutrient removal. To point out a little bit more about those basins, if you look at the north, several years ago, when I actually just started my career in the state as a consultant and designer, we worked with Metro. I was a consultant at the time at these basins. We're using these in terms of a side stream treatment. I'll explain you a little bit more about that. But for any of you interested in process of wastewater treatment? Okay, a few of you. So this is something, concepts that I will explain how we actually innovate treatment that are concepts that you can apply to other things in the future. So if you think generally about what we did with these basins, you can apply that to other things and innovate and name in the future a process after yourself. Because there are still many opportunities like this. So we're using those basins for intensified nutrient removal. We have basins here in the south that we are using to intensified nitrogen removal. And what else do I want to point out? Centrate is very important. Centrate, I want to just put that out here right now in terms of nutrient removal is important because as we bring primary sludge and secondary sludge into the digesters, it's just like your compost pile in the kitchen. You hold it there, you get that after a while, this liquid in the bottom. It stinks, but it's super rich in nutrients. You get nitrogen and phosphorus in there. And if we actually capture that, usually it would be recycled. So about 30% of the nutrient load is constantly recycled in these facilities. If we intercept that centrate flow and pull out the nutrients in that small flow, it's just about 1% of the main flow. It's concentrated and way more lucrative or economic to pull the nutrients out. So that's what we're doing in the south. And I explained briefly how we do that. So this is nitrogen removal 101, very traditionally. Forget right now about the anaerobic zone. We talk about this later, but this is a very conventional, what we call modified Lutzener-Oettinger process, where we are bringing wastewater in. We're bringing with wastewater carbon in. We're removing the nitrate as denitrified. How do we get the nitrate here? Well, we nitrify the ammonia to nitrate in the aerobic zone under air and bring the nitrate back. So this is very traditional, and most facilities today operate in this very fundamental process. So Metro several years ago, and this is just the very traditional nitrate cycle where we have ammonia in the wastewater, we aerate it, we produce nitrate, and then we denitrify it. Several years ago, well, about 10 years or so ago, the science of anamox, which is a different type of bug that essentially uses ammonia, but only nitrite, 50-50, this bug uses both of those nitrogen sources to go straight down to nitrogen gas. We researched that bug for probably 20, 30 years. When I did my PhD, we just started looking at it in soil. And then really in the last 10, 15 years, we figured out how to actually select for this bug in wastewater treatment processes, and now can capitalize on it because the advantage is we're not going all the way to nitrate. We're using way less carbon. Carbon means we can remove more nutrients. We can recover the carbon in terms of energy. We put less air into the system. So there's a number of benefits. And so what Metro did in one of these small tanks that I showed you on the south is, where do we have a lot of ammonia in the centrate? So we're bringing the very high streams. That's something to look out for as a process engineer. You always look for the high concentrated streams and do treatment right at that source. We bring the centrate into one tank. Anamocs are very small, slow growing. So what do we do as process engineers? We put support media in there that we keep in the tank. In this case, it's these noodles. I'll show you a picture of it, but it's just like when you were a kid and your mom made a noodle soup. It's like these noodles on which we are building up these bugs. And so then all we got to do is stop the process as nitrite. We can do that by eliminating what we call the NOBs. So these are nitrite oxidizing bacteria. They are going from nitrite to nitrate. We don't want that because we want to accumulate the nitrite. We do that by pH control and SRT control because they grow slightly faster than the AOBs, so we can wash those out. We've got nitrite and we can do that process. We do that by bringing centrate in, and then we bring that over. The nice thing about this process is it removes already 80% of the ammonia, brings it down to nitrogen gas. We get about 15% of nitrate. That's just the stoichiometric limitation of the process. And we have a far lower load of nutrients on the mainstream. So here you see, for those civil engineers, if you're interested in construction, you see here how this is implemented. This was the tank that was available. You see here the large toads in which we're bringing in that media. This is what it looks like. The reddish biofilm on there, that indicates the anamocs. They're red in color. And then really this is heavily mixed through aeration. We put in aerators on the bottom, and then those are sort of sieves because we got to get the water out, but the media needs to stay in the tank. And so over time we grew those bacteria and removed quite a bit of ammonia with it. So this just shows you when you start out a process, you load it, the Anidamox process, that's what it's called. You load it first relatively low on ammonia loading rate, and then over time you increase the loading rate and remove more of the total inorganic nitrogen. That's shown here in red. So we get about 60–70% removal. And I think by now we're up 80–85. So one other intensification step that Metro implemented, which is, I think, really cool. It's actually a very similar way of thinking. So I showed you this zone. This is an anaerobic zone, meaning we have no nitrate, no oxygen, and we need that in conventional nutrient removal because we know that the bugs that love to take up phosphorus in excess, because we want to remove the dissolved phosphorus from wastewater. There are bugs that take that up in excess, but they need to be exposed to anaerobic conditions, meaning no nitrate, no phosphorus, in which case they take up a lot of carbon. They actually, in this zone, ironically, they put out stored phosphorus that they have, but when these bugs get then into the aerobic zone, they take up excess phosphorus. So interesting bug. If we design as engineers this zone into the mainstream treatment, we need about 15% of the basin volume. And we are exposing essentially these bugs to a concentration of these of the biomass, let's say around 3,000 milligrams per liter. This is a typical what we call mixed liquor. Sounds better than it looks. Mixed liquor is what we call the witch's brew, where we have these bacteria, we aerate it, it's essentially sludge. and the concentration of which is about 3,000 milligrams per liter. If we were to do the same process at, let's say, 6,000 milligrams per liter, what would that do to our to the volume we need? Anybody? I put it in half. Okay, so now we can do double the treatment in only half the reactor size. It's great because now we have capacity, or we can do other things with that volume. So footprint is for many utilities, because we're growing in the state, we need that capacity in our basins. How do we get to 6,000 milligrams per liter? Well, we actually have in our treatment process a stream where we have 6,000 milligrams per liter. It's again closer to the source. So the clarifiers where we're putting what I call mixed liquor in, comes in with 3,000 milligrams per liter. We get a concentration factor of about 2 in clarifiers, 2.1, which means the TSS out of the clarifiers is about double of what we're putting in, because we're settling the stuff, we're concentrating the sludge. So an intelligent person, I don't know who it was, but thought, well, why don't we just move this zone out, put it into a zone where we bring in what we call the return activated sludge and expose the biomass to 6,000 milligrams per liter. So there's one other ingredient we need. We need the biomass that comes in, but we also need the carbon, right? So I mentioned that these bugs, they like the candy food, so the volatile fatty acids, that really gets them going and their metabolism. So somewhere we need to get the carbon in. And the neat thing at Metro is, this is now a side view of the same area I showed you earlier. These are actually the basins we are using because we bring the RAS from these clarifiers directly into that zone. The carbon comes from here. These are gravity thickeners. What we do in gravity thickeners is we take the primary sludge. So when wastewater comes in, one of the first treatment processes is also a clarifier, where we remove a lot of the carbon that we bring in with toilet paper, your kitchen stuff, right? All of that, very carbon rich. We put that sludge into the primary, into the gravity thickeners, and we let it sit there. Again, fermentation. So the carbon is being broken down. We have a lot of VFAs, and it was conveniently very close to this basin. So all we do is we let that sludge settle in there a little longer, several hours. We let that sort of ferment or decay, and we bring the supernatant from these clarifiers over into that basin. And it worked out. We didn't know whether it would work out 15 years ago, but we tried it. It was relatively minor modifications with some piping. But within days, when Metro did that switch, phosphorus dropped below 1, which was really exciting. And the benefit, again, was that we have now only 2 zones that have anaerobic treatment. We concentrated in side stream treatment instead of going into each of these basins. These are 3-pass basins, but we have 12 of them. You would need to go in and modify each of these basins to put a bathable zone in, put mixers in, and make them anaerobic. So it was from a design, from a construction, and from a process, a very slick and elegant solution to implement phosphorus removal. Here's some data from that. So improvement in the north, effluent total phosphorus in 2013. Those basins hadn't yet been implemented. So the median, we were over 1 milligram per liter. The utility needed to get below 1. I showed you this earlier. And with the implementation of that side stream treatment process, we dropped below 1. Pretty courageous, because there were only very few, I think 2 other facilities at the time who had a similar process. So now we had phosphorus removal, but the trouble started. It just started elsewhere. When you have phosphorus removal, we call that enhanced phosphorus removal. We're creating now, the bugs suck up the orthophosphorus. Where do they go next? In the secondary sludge. Where does that go? Into the digesters. The digesters, I explained to you, they, it's anaerobic. We have anaerobic digesters. So all that phosphorus is again excreted from the bugs. So now we have a lot of orthophosphorus in the digestate, what we call it. And phosphorus, magnesium, we always have some magnesium. I also said we had ammonia, which is released. That is just a vicious combination and forming struvite. Struvite is a mineral that settles when we exceed the precipitation point from the chemistry. It precipitates in pipes. It precipitates specifically where we have high pH concentrations. And so what we found is that a number of utilities, not just Metro, that have implemented BioP, have created these types of sedimentation and buildup of struvite in pipes, in valves, in centrifuge bowls. It's not fun for operators and for maintenance staff. So we needed something to intercept that. And so it's sort of a very quick history of BNR that many utilities, not just Metro, goes through. So the next generation of what we are focusing on in the industry and what Metro and Fort Collins, they were the first to implement this technology about 8 years ago in Colorado, is we need to intercept that the phosphorus actually builds up and creates struvite unintentionally. We want to have struvite intentionally because it's a really good fertilizer. Very slow release. If you ever get your hands on it, if you come to Metro, I can show you where we store it. Get your hands on it, put on your tomato plants. It is a really good fertilizer. But we want it intentionally removed so that we don't have to scrape it out of our pipes. So how do we do that? We take the digestate, we put it into that large reactor that you see over there. It's actually the largest reactor we have, I think, in the world. Amsterdam is very large too, but I think this one is larger. So we put it into that reactor. Now we need to form struvite. How do we do it? We put magnesium in form of magnesium chloride. We need to get the pH up. So we aerate it. What does aeration do? It strips out the CO2 that we get through the decay of biomass in the reactor. And so we're intentionally forming struvite in there. And the struvite can be recovered. It looks like sand. I don't have a photo of it. Yeah, this is just make-believe, but it actually looks like you're walking on a beach sand. It looks like that. And it's good. We give it to Ag 1. Unfortunately, we don't get any money for it. I want to change that. They mix it under their fertilizer, sell it, and consumers enjoy a good product. Here just showing some dosing and some effect of that. So when we go into this reactor with the digestate, we have centrate concentrations of about 500, 600 milligrams of phosphorus. Without recovery, when we started the biomag reactor, the MagPrax reactor up, that's just the name of that process, MagPrax, mag for magnesium, we lowered it to about 200, and you can see all of that is a function of how much magnesium to phosphorus we actually dose in the system. If you're an engineer, you do that. This is what Metro did. Process engineers, they did a sensitivity analysis. Which one would you pick? Which magnesium dose would you pick when you see that result? Don't let your professor answer. Come on. Are you a professor? Okay, anybody? Venture a guess. Okay, maybe I need to explain what this is. So this is the phosphorus that comes in the digestate. Depending on if we don't treat it, you get about 250 milligrams per liter worth of phosphorus that just goes through, and that is available to form unintentional struvite. We want to get rid of the phosphorus, so here we dose magnesium to phosphorus at a ratio of 0.7, and that's the effluent phosphorus we get out of the reactor. Here we increased it to 1.4 magnesium, so the more we put chemicals in, we form the pressure to actually for phosphorus to precipitate, and then we tried 1.7. Which one would you use? You would use this one. And why? This one. I love your thinking. And I wish you would have been at Metro 10 years ago or 8 when they started it up. because what Metro did is they picked this. And the rationale was it's the sweet spot, it's the lowest point. So we come out with 30 milligrams per liter of orthophosphorus. It's great, we're good, the reactor works really great. The problem that we had over time is just what you said. We put more chemicals in for once, you're doubling it, you get a marginal relief of that. We have another problem with it because we're putting so much magnesium in that not all of the phosphorus and the struvite is actually built up and removed in that reactor. So now we're carrying excess magnesium outside of the reactor, and we saw that we still had struvite issues outside. And really what we are, and this is also important for engineers because we are at a point where we, as engineers, process engineers, we're pretty good at optimizing one process with one cause-effect relationship. We're pretty good at that. And, we've got wastewater figured out. What we are not yet good at is actually looking at a more complex, multi-objective optimization. What we're really after is we want to meet our effluent. We could meet our effluent here, here, or here, right? That doesn't tell us if we're meeting the effluent. We need to lower the O&M costs, and you're exactly right. We're putting double the amount in for what benefit. We need to minimize the struvite nuisance outside of this reactor. And to make things even more complicated, but also interesting, how much we are precipitating here is actually a lot of impact on the downstream dewatering of the digestate, because we're adding multivalent cations in, and without going into the exciting science of that, it has big impacts on the polymer addition. Polymer is a chemical, very expensive, that we put in to dewater the biosolids. And there is a very interesting synergy of both of these. And so we also need to look at the whole cost of the solids handling, which is what we're doing this year. We're focusing on that to figure out where actually the sweet spot is. And the sweet spot is actually even lower than 0.7, it turns out. It's probably somewhere around 0.6, where we just hit all of the sweet spot for everything. So that was actually already a new frontier because we're sort of in the second phase of optimization. We got new treatment processes, then you optimize the one treatment process. We did that 6 years ago. And then you take a look at it again in a larger context and figure out that we can still further optimize where we are operating and how we do things. So I want to switch a little bit and talk about regulations for those of you who are interested in that. So the state had put out pretty early, I don't know exactly when, but probably somewhere 10 years ago, we had the discussion, what do we do after Regulation 85? How do we get closer to the nutrient standards in the South Platte and other surface waters that we have? And how EPA, the state, looks at it, it says, well, we have standards. These are not even yet the standards that EPA approved. These are, we call them interim standards that EPA accepted. EPA actually thinks these standards for the South Platte should be even lower. So then we need obviously some transition time. In the meantime, we as utilities and as engineers are thinking about how the heck are we going to meet those limits? And what technologies do we need to put in to actually meet these low nutrient requirements? And for all of you who may come from the source water side or the resource side and South Platte, and yes, we do have issues with eutrophication. I just want to maybe broaden the perspective of how challenging it is and what we all need to collectively think about, how we actually move in a sustainable fashion to lower nutrient limits as we move forward, because there are limits of technologies. I will talk about that because there's still room for improvement in what we're doing right now, secondary treatment. But we need to be aware what it actually means to put regulations in place for utilities, because we may push us into pathways of technologies that are not sustainable, and we create actually more environmental harm than we're benefiting if we're just looking at one endpoint, the nutrient concentrations in the receiving river. So essentially what these concentrations mean, we did as Metro a facility plan in 2018 and asked, well, we got to prepare for this. What do we do? So I mentioned earlier, we have nitrate, ammonia in the water. We also have what we call organic nitrogen and phosphorus in the water. And all of them add up to what we're currently discharging, which is about total inorganic, total nitrogen of about 7, and total phosphorus of about 0.3. And just long story short, in order to meet with what we know existing technologies can do to meet those requirements, Metro would need to put on 6 new treatment processes. 6. We already have right now about 6 liquid stream to get us from about 35 to 7 in nitrogen, and to go from 7 to 2, 5 more milligrams, we got to double the number of treatment processes we have right now. We got to remove the residual ammonia, the residual nitrate. We got to remove dissolved organic nitrogen and dissolved organic phosphorus. And so there's a number of treatment processes that we would need to actually achieve that. In the meantime, we put a lot more energy in. We probably double the energy we put in. And we have a lot of chemicals we put in. And chemicals means also for the removal of those, we're increasing the salt concentrations. And we haven't even started to really manage salt in our waters. And everybody, I don't know if you're working on the South Platte, but then you know the salt concentration builds up with every mile in that river. Please.
You mind if I ask a question?
Yes.
So is standards for the Rec 31 are the stream standards?
Yes.
It's stream water quality standard. Do you have flexibility in terms of attaining maximum concentrations during the year? Because again, during very high flow conditions, we not need anywhere close to that level of treatment.
Yeah.
Because ultimately the amount of the concentration in the river will be at those levels.
Right, for dilution.
Treatment.
Yeah, so very good question. I did not, for brevity, this daily max here only refers to ammonia because that's an acute limit for ammonia. The daily max does not refer to the regulation 31 nutrient criteria. We don't know for sure how they would be implemented, but when I ask the question, I usually get the answer it would likely be on an annual median. And the rationale being that a 1-day spike of phosphorus in the river may not grow immediately algae, but distributed over seasonality, longer periods of time, we need low concentrations to inhibit eutrophication. So yes, so there is some flexibility to your question. It's not implemented on a daily max basis, but still on an average over a year to stay below those limits, it's challenging.
Those limits are not the effluent concentration levels or the stream, downstream.
Yeah.
Ambient water quality.
So, okay, very good question. I didn't mention that either. These are standards, and standards mean we need to stay in the river or in the surface water, whatever reservoir. We need to stay below those concentrations. And so there is a calculation on what we're discharging. If you have dilution, you can have higher effluent limits because dilution still brings the river to below the standard. In our case, I mentioned that at the beginning, the South Platte, if you're down at, and you're doing that bike ride along the South Platte, you see a lot of sandbanks upstream of where we discharge. We are pretty much, I don't know if you ever did that ride, but it's really interesting. Just looking at the river, we are just where I said Sand Creek is coming in on the bike path, and up to our discharge point, it is essentially dry for large amounts of the year. So our discharge requirements have zero dilution, and we essentially need to meet the standards end of pipe. There are a few other utilities in the state that have that situation where we are essentially the in-stream standard is end of pipe. So time check. How much? How many? 20. Good. I think that's fine. And please keep asking. Are there any other questions? I'm rambling a lot. I'm not sure if I'm rambling, but please.
Yeah, that, how much nutrient adds to the average household monthly cost for wastewater? I know it's an awful different kind of question.
You are the second person today who asks me this question. We as Metro have this number. because we are charging our connectors based on the cost of hydraulic treatment, BOD, and nitrogen treatment. And so we actually calculate the cost for nitrogen removal. I can't tell you this number right now for us. I give you a rough order of magnitude. For complying with Regulation 85 limits, take city of Fort Collins. They actually had already a nutrient, but of the size of this city. Let's say you have a 20 MGD you're producing in the city, 20 MGD of wastewater. For that facility to implement the basic BNR that I showed you earlier, it would probably be a cost of 50 to 60 million. So you have how many, 200, 300,000 people here? You could calculate 125. So you could do the math on that.
How many million was it?
I would say basic BNR, 50 to 60. Yeah, because you got to increase the aeration basins. You have some other stuff you got to do. And I think the whole construction would come down to that. And it may actually be higher. No, that is just the construction. It's probably even higher by now because prices have gone up. That only gets you to here. This is significantly more expensive. For Metro, we calculated as part of the facility plan with everything we got to do on the tertiary side to comply with that, it would be over $1 billion, which interestingly, still CDPHE would look at those and say, this is doable. Because you got to calculate it on, for the whole connector area. For us, really, it is a high cost, but it's also, Metro makes the point, look, we're putting a lot of chemicals in. We're putting a lot, and we're going to have in the future, probably salt limits for sulfate and chloride. They're got to come at some point. We are intensifying our population so much that at some point we can't meet the drinking water standards anymore with the water we put into the river. We're putting a lot of energy in, and for what marginal benefit? We don't even know yet what that additional benefit is, and is this really the right location where we need to remove it? And a major technical challenge we have is in the timeline that CDPHE required us to do it. We need to do other improvements to even be able to put tertiary treatment in that we could never engineering-wise do in that timeline. So there's a lot of challenges. And we weren't the only ones. A number of utilities brought that point up. And before we have a collective lawsuit against CDPHE, they did agree to a third-party assessment of what is actually technically feasible. It works under the whole work group of feasibility. It's a feasibility assessment right now where we collectively employed a expert panel under NWRI, which is just an organization that provides this regulatory support. And that study just came out this week, actually, as a draft. One of the major contentions we had or decisions we needed to make in our state is whether we should actually employ reverse osmosis membranes for treatment in the future, because these limits, really the technical feasible way to get there is through ROs. But now we have concentrate that we don't know what to do with. We can't inject it. We can't put it out. We have already water rights limitations. We don't know what to do with it. And it will be interesting because the expert panel explicitly says in their report that regulators should not put regulations in place that require utilities to use RO in the future. If CDPHE was to accept that, that will be already a very interesting gateway decision for our state in terms of meeting those requirements and how we implement permit requirements